Okay, let's think about tabular data. Now, I know what you're thinking. It sounds so dry, right? Like financial ledgers and just endless spreadsheets.
It does, but that's where the most critical prediction problems are actually happening.
Exactly. These rows and columns, they dictate outcomes in, everything from economics and drug discovery all the way to national security. And for 20 years, if you were making predictions with that data, the rules were basically set in stone.
Oh, they absolutely were. If you were a serious data scientist, you know, tackling classification or regression on structured data, you weren't really looking at the latest deep learning thing.
No.
You were reaching for the proven stuff,
Mm,
the battle-tested models, gradient-boosted decision trees.
yeah.
Talking about the world of XGBoost and CatBoost.
And deep learning just couldn't get a foothold, right?
Not really, because tabular data sets are they're messy, they're heterogeneous, you have mixed feature types, different scales, missing data, noise. That messiness was always the Achilles heel for deep neural networks.
So you had this whole domain where the sort of old school hand-engineered statistical methods were the undisputed king simply because the data was so unique.
Right.
But now, for this deep dive, we are looking at a new contender. It's called TabPFN, the Tabular Prior-data Fitted Network. And this is a foundation model that's claiming it can overturn 2 decades of dominance.
That's the claim, and that's our mission today, to really dissect it. And honestly, the research material suggests this is a genuine paradigm shift. TabPFN isn't just tweaking the rules.
It's changing the game.
It's changing the game entirely. It moves us away from hand-designed algorithms to an algorithm that it's self-learned. And the results, they show it's not just competitive, it's dramatically faster and, well, more accurate.
That idea, a learned algorithm, that's the real breakthrough here, isn't it? We've seen this pattern before in AI.
We have.
We saw learned convolutions replace things like SIFT and HOG and computer vision, transformers replacing grammar models in NLP. TabPFN feels like the same thing, but for boring old spreadsheets.
It's the next logical step for end-to-end learning. And the engine behind it all is something called in-context learning, or ICL.
The same mechanism that powers LLMs.
The very same. The success of large language models is built on this.
Okay, so let's unpack that. How does in-context learning apply here when we're dealing with numbers in rows and columns instead of, words in a sentence?
Well, the big difference is how you approach the training. With traditional methods like a boosted tree or even a standard neural net, you have to train a specific model for every single data set you work with.
Right. You feed it data point by data point, you tweak the parameters.
Exactly. You get data set A, you train a CatBoost model. You get data set B, you train a whole new CatBoost model.
A completely separate process.
TabPFN just throws that whole idea out. It is a single, pre-trained network that acts as a general-purpose learning algorithm. It was trained only one time across a massive catalog of synthetic data sets.
How massive are we talking?
The researchers use something like 130 million synthetic examples to train it.
Wow. So the model isn't learning the data in front of it, it's learning how to learn from data in general.
That's a perfect way to put it. And it completely changes the workflow. At inference time, when you have a new real-world data set, you just feed the whole thing to TabPFN.
The whole thing. You mean the labeled training data and the unlabeled test samples?
All at once. It doesn't have a separate training phase anymore. The training and the prediction all happen in a single, super fast neural network forward pass. The new data set is just context, like a prompt for an LLM.
Okay, but to handle that context, a 2D table instead of a 1D string of text, they must have needed a pretty special architecture.
They did. They leveraged the transformer architecture, of course, but adapted it for tables. The key innovation is this really clever two-way attention mechanism.
So it's not just looking at the sequence.
No, it has to look in two directions. It pays attention across the features, so across the columns in a single row, and it pays attention across the samples, looking down the rows to find patterns. That dual attention is what lets it understand both the relationships between columns and the relationships between different data points.
That architecture sounds incredibly powerful, but its entire capability really depends on its education, right? Let's talk about that education, the 130 million synthetic data sets, that manufactured training diet. That has to be the secret ingredient.
It is, absolutely. The model performs so well because it's basically seen every possible small tabular data set that could exist. And by doing this, the researchers completely sidestepped all the usual nightmares of real-world data.
You mean like privacy, copyright, test data getting mixed in with training data?
All of it. They just built their own synthetic world to train in.
And this wasn't just random numbers. The data was generated using something called structural causal models, or SCMs. What does that actually mean for the listener?
An SCM is basically a formal way of defining the rules of a synthetic world. It dictates cause and effect, how one variable influences another. So instead of just generating random numbers, they could actually program the desired algorithmic behavior into the learning process.
So they'd create a blueprint, a map of a realistic data set, using a directed acyclic graph, a day.
That's right. The day specifies which features influence other features, creating this complex web. And the generation pipeline would sample high-level things like the size, the complexity, the number of important features. But then they made it even more realistic.
This is where we get into the weird math, right? The use of small neural networks with things like sine and modulo functions.
Exactly. Because real-world relationships are almost never a straight line. If you're modeling, say, engine vibrations or economic cycles, you get these weird nonlinear patterns.
Physical things.
Right. So using sine, modulo, and other nonlinear functions forces the generator to create data sets with those chaotic, messy patterns you find in the real world. It ensures TabPFN learns the hard lessons up front.
And those hard lessons include all the data imperfections, the stuff that used to break deep learning models.
Precisely. They deliberately baked in challenges. Missing values, huge outliers, completely useless features that are just random noise. By forcing the model to solve millions of these broken synthetic tasks, it autonomously learned how to handle it. It learns to ignore noise and manage missing fields without any human telling it to.
Okay, so that brings us to the results. The quantitative proof. The sweet spot for TabPFN is on these small to medium datasets, which they define as up to about 10,000 samples and 500 features. This is where the headline numbers come from.
And it is a stunning comparison. Just take a classification task. TabPFN's default out-of-the-box configuration took just 2.8 seconds.
2.8 seconds to do what?
To load the data, train via that forward pass, and predict the results. And that outcome outperformed the industry standard baselines, like CatBoost and XGBoost, that were given 4 hours of hyperparameter tuning.
Wait, 4 hours versus 2.8 seconds. Let that sink in for a second. That's a speed up of over 5,000 times for classification.
And about 3,000 times for regression. If you're a data scientist running hundreds of experiments, this collapses your iteration time from days down to minutes. It's a revolution in workflow.
And it's robust, too. It's not just a speed trick.
No, the robustness tests were really telling. When they deliberately sabotaged the data sets, like multiplying important features by random numbers to create huge outliers, TabPFN's performance barely budged.
The detail I found really compelling was about the training efficiency. It speaks to how much prior knowledge the model has.
Yes, it showed that TabPFN, even when you only give it half of the training samples,
Only half the data.
it still achieved the same accuracy as the next best traditional method that got to use all of its samples.
Yeah.
It just starts with such strong, generalized knowledge that needs way less new data to master a task.
Okay, now let's talk about a critical feature for high-stakes modeling, uncertainty. Most regression models, they just spit out a single number.
A single point prediction, yeah. TabPFN is different. It gives you a whole target distribution. So you don't just get the prediction, you get a quantifiable sense of the model's certainty.
How certain it is about that prediction.
Exactly. And to show this off, they use the classic double-slit physics experiment, which creates these incredibly complex multimodal intensity patterns.
Right, trying to model the exact density of light hitting a detector. That's a really intricate problem.
It is. And TabPFN modeled these weird non-Gaussian distributions perfectly in only 1.2 seconds. To get a similar result with traditional methods, you'd have to do this complex manual setup of training multiple different models, and even then, the results were way worse.
So this is huge for fields like, say, clinical trials or risk assessment, where knowing the uncertainty is just as important as the prediction itself.
It's a game changer there.
Let's move on, because the capabilities of TabPFN really make it feel like a true foundation model, not just a faster predictor. It changes the whole toolkit for the data scientist.
It really does.
Yeah.
Because it learns the fundamental feature distributions, it unlocks a whole suite of things that tree-based models just can't do. Not without heavy customization, anyway.
So let's start with data density estimation. Why is knowing the probability density function, the PDF, so important?
Because if the model understands the PDF, it knows what normal data looks like. So if a new data point comes in that's way outside that normal high-density region, TabPFN can flag it immediately.
Which is the basis for anomaly detection.
Exactly. Identifying credit card fraud, spotting faulty sensor readings, signaling that a piece of equipment is about to fail, all that stuff.
And because it understands the data so well, the architecture is also naturally generative.
Yes, it can perform synthetic data generation. It can look at a real-world data set, like the German credit data set they used, and then generate new, completely artificial records that mimic its statistical properties.
Which is incredibly useful for data augmentation if your data set is small, or for creating privacy-preserving data you can share.
And here's where it gets really powerful for advanced users. Reusable embeddings.
Okay, what are those?
Unlike a decision tree, which is a fixed structure, the neural architecture produces these meaningful internal representations of the features. They're called embeddings. And you can extract them and reuse them for other tasks,
Like what?
like clustering. They showed that these embeddings dramatically improved class separation on complex data, like handwritten digits, compared to standard approaches.
And the ability to fine-tune. This is a massive difference from the old guard.
Oh, it's a critical foundation model trait. You can't just transfer knowledge between two different tree models. But since TabPFN is a neural network, you can fine-tune it on related data sets. This means you could have, say, a general TabPFN model for oncology.
And then fine-tune it specifically for one hospital's patient data.
Precisely. Creating specialized experts.
Okay, last one on this. Interpretability. It's one thing to be fast and accurate, but in high-stakes fields, you need to know why the model made a decision.
And TabPFN supports SHAP values, shapely additive explanations, which are key for understanding feature importance. But what's crucial is that the sources found TabPFN achieves its high accuracy while learning surprisingly simple, interpretable relationships.
So it's not a black box?
It's much less of a black box than, say, CatBoost, which often learns these incredibly complex, non-smooth decision boundaries that are almost impossible for a human to understand. Here you get performance and accountable insight.
Now, if we zoom out, TabPFN seems revolutionary, but we have to frame it correctly. It's a component, a powerful one, but it doesn't replace domain expertise or data cleaning, does it?
Not at all. That context is crucial. Feature engineering, cleaning your data, understanding the problem, all of that is still vital.
And we need to be really clear about the constraints. Where does its power end, at least for now?
The big one is the size restriction. The current version is optimized for small to medium-sized data sets, that 10,000 sample, 500 feature ceiling. If you're dealing with tables that have millions of rows, you're still better off with traditional methods or something like AutoGluon.
And we have to clarify the speed paradox for the listener. The time to train and predict on an entire batch of, say, 10,000 samples is just seconds. But what about predicting a single real-time sample?
That is the key nuance. While TabPFN is 5,000 times faster for the whole analysis and development process, it's actually slower for single sample inference at deployment. The sources cite something like 0.2 seconds for TabPFN to predict one sample from that 10K context,
Okay.
compared to 0.00002 seconds for a highly optimized CatBoost model.
So it's a revolutionary tool for rapid prototyping, for batch analysis, for getting a great model incredibly fast during development. But it's not yet the tool for, say, high-frequency trading where every microsecond counts at deployment.
Exactly. It's a trade-off. Speed of development versus speed of deployment.
So looking ahead, what's next for this technology?
Well, the researchers are focused on scaling it up to handle larger data sets and making it more robust to things like data drift, where the data changes over time.
Yeah.
But I think the most exciting direction is creating specialized priors.
So learned algorithms tuned for specific data types.
Yes. Imagine a TabPFN specifically for time series data, or for multimodal medical records that combine ECG traces and genomic data. That's the future.
So to sum it all up,
TabPFN is basically confirmation that the foundation model paradigm, which completely reshaped text and images, has now officially arrived for small-scale tabular data. It gives you a mix of speed, robustness, and out-of-the-box utility that has just been missing from this field for a very long time.
the success here really shifts the whole philosophy, doesn't it? It's a move away from humans handcrafting the perfect statistical model toward an AI that autonomously discovers the optimal learning mechanism just by seeing millions of examples. And that brings up a really profound question. What other complex hand-engineered mathematical algorithms that we've always considered immutable, maybe optimization routines in finance or simulation routines in physics, what other algorithms might AI be trained to optimize and maybe even replace next? It changes not just what we build, but the very nature of how we build it.